Swayam Prabha. Digital India. Educated India.
Welcome to this programming coding tutorial today. So till now you have looked at a lot of theory. Today we are going to implement some of the things that you have learned. So basically the code is written in C++, and there is a corresponding wrappers that are written in Python, okay, which will basically call the C++ code. And we will also make use of some Mathematica to do some of the linear algebra, some of the computer algebra calculations, okay. So this entire code was originally written by Professor Geyer. I made some small changes here and there, and then we're going to learn that part of the code, okay. The total code is for a lid-driven cavity, but we are not going to look at the entire code today. We are only going to look at the equilibrium distribution functions only for today, okay. So if you have Mathematica installed on your laptops, you can even try doing things that I am trying to do here, so that you can be on the same page as what I am doing here. Feel free to ask me any questions anytime. All right. Okay. So as part of the code, we have certain time steps where t is going from 0 to number of time steps t plus plus. So there is a time loop that is going on, and then there is a for loop for y, which is going from y equals 1 to number of rows minus 1 y plus plus, and there is another for loop which is for x, which is for loop of x going from 1 to number of columns minus 1 x plus plus. So basically you have a two-dimensional space that is in x and y, and then there is a time loop that is for t, okay. So there is a main loop like this. Within that, now we have to look at, as you know, in lattice-Boltzmann you have two main operations. One is the streaming, the other one is the collision, right? So we will look at the collision operator that is here, that is written out here. For example, I have used F equilibrium 0 0, and F equilibrium M0 stands for minus 0, F equilibrium P0 stands for plus 1 0. So these are all actually coming from your lattice directions. So I use this Jupyter notebook to explain some of the equations and some of the diagrams we have, okay. So how do we calculate the equilibrium distribution function using the moment matching that you have learned in the theory is, so that is the D2Q9 lattice that you have seen already, where you have F00 right at the center, and you have F10 that is in the positive x direction, F minus 10 which we are denoting as FM0, and then F01 that is F0P, and then F0 minus 1 that is F0M, okay. That is the notations used in the code, and these are the four cardinal directions. Then you have the remaining directions, which are F11, F minus 1 1, and then F minus 1 minus 1, and we have F1 minus 1, okay. So these are all the 8 directions, plus you have the stationary link that is F00 at the node center, okay. Then how do we calculate the equilibrium distribution functions from the moments? So you are already familiar with the moments of the distribution functions, right, where a moment MAB was defined as Fij I to the power A times j to the power B, where I and j are, where this Fij I to the power A, j to the power B is summed over all possible I and j directions, right. This is how your moments were defined, where I and j could be from one of the out of these three values, right. It could be either minus 1 or 0 or 1, or it could be j could be again either in minus 1, 0 or 1. That is going to give you all possible combinations here, right, of ij, and your moments of MAB, these indices A and B can go from 0, 1, 2. For example, A could attain values of 0 or 1 or 2, right? If it is a 0 moment, first moment or second moment and so on. Okay, so we have this moment generating function from the distribution functions. Okay, now we want to actually use this moment matching to obtain the values of equilibrium distribution function, okay, to obtain F equilibrium. Later on we will see that we will also use the same moment matching to initialize the values of the distribution functions themselves. Okay, that we will come to that in another lecture, but today we will look at the F equilibrium distribution function. So you are also familiar with for the conserved moments we have M equals M equilibrium for all the conserved moments, correct? And then if you recall, what was M00? What was M00 was density, right? M00 was density, which I have not written here. But then M10 is your linear moment, x momentum, right? That is your rho times ux. And M01 would be rho times uy, correct? The y momentum, okay? And similarly, what would be M20 equilibrium? That means you are substituting for A equals 2 and B equals 0, correct? That means I go back here, I substitute for M A equals 2, B equals 0, and then I calculate this summation, correct? That's basically going to give me, as you have seen in the lecture, rho times CS square plus UX square, right? That is what you have obtained in the theory part. Similarly, M02 equilibrium will come out to be rho times CS square plus uy square, right? That's what we have already written out. Then what will be M11 equilibrium? M11 equilibrium would be product of M01 times M10 divided by the density, correct? So which means basically I multiply rho ux times rho uy divided by rho. That's basically going to give me rho times ux uy, okay? Similarly, M12 equilibrium would be M10 times M02 equilibrium divided by rho, right, which will give me rho ux for M10, and M02 equilibrium is going to be rho times CS square plus uy square divided by, I have one extra rho which will cancel out the second rho I have, okay? Similarly, you can write down the M21 equilibrium as the product of the two moments, that is M20 and M01, correct, divided by rho, which will give you rho times uy times CS square plus ux square. And then we have M22 equilibrium, which is again the product of M20 and M02 divided by rho, okay? That will give you rho times CS square plus ux square times rho times CS square plus uy square divided by rho, which will cancel out one of the rows, okay? So these are the moments that we have learned in terms of the macroscopic properties, right? The rho, ux, uy, and the speed of sound, okay? Yeah. Yeah, sure.
Save the microphone, please.
Yeah, you can use the speaker.
So while computing M21 equilibrium,
M21 equilibrium, yeah.
we considered M20 equilibrium, but M01 is not at the equilibrium.
Oh, M01 is the moment, the momentum, correct?
Yes.
Is M01 a conserved moment or not? It's
Oh,
a
they are
conserved
already
moment.
at the equilibrium.
Yes, that is though I didn't write it. We can write it as M10 equilibrium there. I think I missed to write it as equilibrium there.
I mean, you don't need to write it as equilibrium. One interesting addition to this that you could discuss is if momentum is not conserved because you have a force, in that case, actually what you would have to do is what we learned today in the lecture with this overbar version. You would have to take the average between the one before the collision and the one after collision. Yeah, so you would have to add half of the force so that you are in the middle of this, in case this would not be conserved.
Yes,
Yeah.
yes. So this is about the moments, how they are related to the macroscopic properties. Now we have to basically work with this particular equation in terms of expressing the moments into the distribution functions, okay? So for that I will launch Mathematica. Okay, I have something up here. Let me write this again. Okay, just to be clear. So we have moment a underscore comma b underscore. Okay, that is the moment I want to define. Okay, which is basically equals summation of I and summation of j, fij, I to the I and j to the b. Okay, I'm going to use, initially I'm going to type a few things, then I have things that I have already typed up which I'm going to reuse here. Okay, so what we say is that we have a summation, okay, and then we have another summation. The first summation is on let's say the inner one is on I and the outer one is on j. Then we have a sum of I to the a, right? Okay, so I have I to the a, okay, times j to the b, right? That's what I have, times f of ij, right? That is the summation, okay, that we want to calculate. Okay, and then with I going from -1 to 1, and then we have j going from -1 to 1. Okay, that's what I want to calculate. Yeah, so oh, I have put brackets here, and then j going from -1 to 1. Okay, so that's what we have. Fine. So is everybody okay with this, what I have written? I have basically translated this MAB equals summation of I, summation of j, Fij, I to the a, j to the b into here, two sums, I to the power a, j to the power b times Fij, where I goes from -1 to 1 and j goes from -1 to 1 in steps of 1. So -1, 0 and 1. Okay. Okay, so I define that. Then I would like to calculate what is moment of 1 comma 1. Okay, so I am substituting for a underscore and b underscore. A underscore basically refers to this a I have used, and b underscore refers to b. Okay, so whatever you pass as arguments there are going to be used here. So moment 1 1 it has printed out here as f of -1 -1 minus f of -1 -1 and so on, right? You have 4 values it has printed out. Yeah, so it has printed out as all these 4. Is this correct? Can we verify? We can substitute for a equals 1, b equals 1, right? When you have I becoming -1, and you would basically get when you have 1 1 here, I becomes, let's say whether I and j, if they become both negative or both positive, then you're going to get the positive value, correct, for the factor. Okay, and if there is one of them is minus, then that minus will come into play here, right? So you see that this is f of -1 -1 plus f of 1 1, and the other two values which are f of 1 -1 and -1 1 have minus in the front. Okay, what about I equals 0, j equals 0? That basically becomes 0 to the power 1, 0 to the power 1, which is basically 0, correct? Similarly, when I equals 0, all other values of j also are zeros, right? Because you are multiplying with that, or become 1, right? So that is there. So you only basically survive with these 4 values, correct? Okay, so let me then type up what is moment of, so instead of 1 1, let me look at what is moment of 1 0. Okay, now we run into some trouble here. It says the moment I put b equal to 0, it shows that j to the power b, when j becomes 0, is 0 to the power 0. It says indeterminate expression, I cannot determine this, right? So what we do is we use a small trick here. Maybe let's add some small parameter here, which is called some temporary value of aa. Okay, so we are not raising 0 to the power of 0, rather we are raising some small value to the power of 0, and then we tell Mathematica that this value is actually tends to 0, it's a small value. Okay, so what we do is that as my A tends to 0. Okay, so with that we are able to make Mathematica calculate or evaluate 0 to the power 0 as 1, okay, with the small epsilon that we have added, okay, and it gives you, let me say if you have M10, right, that means A is 1 and B is 0, okay. When B is 0, what do we have? This is 0, so anything that you get for J are all to the power 0, they will all become 1, correct? Okay, so what we have basically here is then for I going from, that means for any value of J you are going to get only positive values, but then depending on the value of I, the positive or negative is going to be determined, correct? So for example, here you see we have out of the 9 possible values, you only have 1, 2, 3, 4, 5, 6, only the 6 have survived. That's because your B is raised to the power 0, correct? B is 0 here. Do you see what I am trying to say? Correct? Okay. For example, if I say M00 calculate, then how many values did we get? We get all 9 there, right? I to the power 0, J to the power 0, correct? So that's basically giving you f of minus 1 times minus 1 to the power raised to 0, minus 1 to the power raised to 0, which is 1 and 1, right? That's a plus 1. And then when I and j is minus 1, 0, that is also a plus, right? Similarly, whatever is the value of I and j, your a, b will always make it to be positive. And then you get sum of all the distribution functions, that is your density that you have learned, which is M00, correct? So similarly, we can now of course generate all other possible moments in terms of the distribution function. So I could write moment 0, 2, that is basically giving me this sum of the distribution functions, right? Okay. Is everybody following me? Questions on this? This is exactly what I have shown now, right? We have defined moment equals sum of I to the power a, j to the power b, fij. That's all we have done, okay? So we have done till here. Now what I want to do is that we want to generate all possible moments, right? All possible moments are moment of 0, 0, 1, 0, 0, 1, 2, 2, everything that we have seen in the Jupyter notebook, right? So we want to generate all these moments, but unlike what I have written here, we want to generate them in terms of the distribution functions f, right? As in coming from this expressions. Okay, so that means we should look at so essentially now moment of AB, I am making it equal basically is an equation where is equal to MO of AB, okay. So MO of AB is I am defining as a variable, okay, whereas moment of AB is the function that I have defined before, right. Moment of AB is the function I have defined here, and that will be evaluated in terms of distribution functions f, and that will be assigned a value of moment of that particular AB value, okay. And then A and B, now just like we have done previously for I going from minus 1 to 1, j going from minus 1 to 1, here we are saying A goes from 0 to 2, right, essentially 0, 1, 2. Similarly, B goes values of 0, 1, 2. So we are going to generate what will be all these moments, and we are going to call them as MO of that particular AB, okay. And then we are storing all these in a table format, because now we have several equations, right? Okay, so if I were to just run this one, okay, it has executed this part. Okay, what it basically did is, as you can see, it has stored in M00, moment of 00 equals summation of all the distribution functions, f's, correct, which is the same as what we have done before, just the density equals this. Now moment of 0, 1 equals these values, correct. And then similarly you see you have moment of 0, 2 is up till here, So you have all these equations written down in a list of lists. Okay, that's what this table has done in putting them up. So you have m10, you have momentum of 1 1, moment of 1 2, then you have moment 2 0, moment 2 1, and then moment 2 2. Correct? So we have all these things that are developed. But then what we would like to actually do is we would like to calculate. Right now what we have is we have distribution functions, some of the distribution functions written in terms of as moments, right? But then we would like to calculate what will be the distribution function, a particular distribution function in as expressed as different sum of the moments. Okay, right now I have moments equals distribution functions, right? I want to do the inverse. Okay, so what I will do is for that I will come back here. Okay, so I will write we have this table which is moment of AB equals MO of AB. This is exactly same as what we have seen before. Okay, only thing is that I have written flatten. Flatten is going to take away one of the lists that we have. Okay, otherwise it's going to be a list of lists. And then we say solve, and then and keep it here. Basically what this has written is this is exactly same as what we have written before, except that it has m00 is arrow to the distribution functions. Okay, now I want to show how I think some of you are familiar with Mathematica. So how do we solve for any a small equation? Let us say I have this. I have a quadratic equation x square plus ax plus 1 equal to 0. That basically expresses that this is the equation we want to solve, and I give x here, right? I have already solved it here. Okay, so if it is removed. Okay, so that means it basically solves for x from this equation, and it's giving me x equals minus square root of a square minus 4 by 2. Similarly, other value of x goes to minus a plus a square minus 4 by 2, right? It's giving me that. Similarly, let us say if I want to solve for two variables, then what should I do? I write solve with ax plus y equals 7, that is the first equation. Then I have bx minus y equals 1, that is the second equation. And in the parenthesis, in the curly braces here, I am going to give x comma y, correct? So this x comma y is now will be solved for x comma y, and it's going to give you x equals some 8 divided by a plus b, y equals minus a minus 7b by a plus b. So it has given me these two. Now on a similar note, I want to solve for f00, f11, f minus 10, and all these things as a function of the moments that we have. Okay, so what should I do? I should also write a solve, but then where my equations are specified in the first part, and in the second part I should list out all the distribution functions f's. Okay, if I can do that, then I can make Mathematica solve for these distribution functions. That means I will write just like what we have done before, solve, okay, flatten of table of moment equals moment of AB, where A and B each go from 0 to 2. Okay, so this is A goes to 0 to 2, B goes to 0 to 2, and then we have the flatten is there, then comma, then I have what will be the variables that I have to solve for. I am looking for solution of f00 and so on, right? Those are nothing but fij, where I goes from minus 1 to 1 and j goes from minus 1 to 1, right? And then again this is a table which I am flattening and giving, and I am saying these are the set of equations, comma, these are the set of variables I want to solve from these equations, that these equations contain these variables which I want to solve for, right? So let me just delete this, okay, and then try to run this. Hopefully it will run. Okay, so it has run. It has given me, it has solved for all these equations, and then it has written f minus 1 equals 1/4 of moment 1 1 minus moment 1 2 minus moment 2 1 plus moment 2 2, right? It has given me f's in terms of the moments, correct? Similarly, f minus 1 0, it has given me half of minus moment of 1 0, 1 2, 2 0 and 2 2, okay? Similarly, it has also given me distribution functions f minus 1 1, okay, and f0 minus 1, f0 0, f0 1, f1 minus 1 and f1 1, okay? It has given me all the distribution functions in terms of the moments, okay? Now we want to actually calculate the equilibrium distribution function f in terms of the equilibrium moments, correct? That is what we kind of started off doing with. So in order to do that, I'm going to, because again you see there are two curly braces here, we want to get rid of one of them so that it will be just a list instead of a list of a list, okay? So let me define this entire thing as some ffs, okay, that is the distribution functions, and we use this double square brackets 1 here to get rid of one of the dimensions, okay? So basically it will become, if I don't have this, then it's going to be list of lists. So I am using square brackets 1 to basically give me just a list out of that, remove the outer curly braces, okay? So that is going to give me that, but then we also realize that out of all these ffs that are now stored into this ffs, right? So if I do this, it is storing all these values into this variable called ffs, okay? It has stored all these things. Now what should I do? What will I do is essentially in this ffs list I have, I'm going to substitute for or going to replace for moment of 0 0, correct? Moment of 0 0 is nothing but what? Rho, right? Density. So I'm going to write it goes to rho, and moment of 1 0 is rho times ux, correct? And then moment of 0 1 is rho times uy, okay? Then moment of 2 0 is rho times cs square plus ux square. Cs square is 1/3, okay? And then similarly moment of 0 2 is your rho times cs square plus uy square, okay? And then moment of 1 1 is rho times ux uy, and moment of 1 2 is rho times ux times cs square plus uy square, okay? Then we have moment of 2 1 is rho times uy times cs square plus ux square, okay? And then moment of 2 2 is rho times cs square plus ux square times cy square plus uy square, right? That's what we have. So I'm going to ask Mathematica to substitute for all these MO 0 0 1 1, all these values in terms of these variables which are my macroscopic variables, right? The rho, ux, uy and so on. So it's going to do that, and it's going to give me the equilibrium values of f minus 1 as this quantity, right? That is 1/4 of, it has replaced all the moment values we have obtained before. For example, we can go back, minus 1 was earlier in terms of moment 1 1, 1 2, 2 1 and 2 2, right? But then it has replaced it with whatever we have said, and it has written this as 1/4 of rho times ux uy minus rho times 1/3 ux square times uy minus, so these are basically the same expressions we have used before, right? It has just substituted for all of these. Similarly, f of minus 1 0 is in terms of, again in terms of rho ux uy, and f minus 1 1 also is like that, f0 minus 1 is also like that, and you see density f 0 0, the equilibrium distribution function for f 0 0 is also in terms of all these values, okay? So we got a big list of distribution functions in terms of rho and ux uy. Now for the same thing, I'm going to basically substitute into this, these substitutions I have done before, I'm going to capture them into a variable, okay? That variable, let us call it as ff equilibrium, which basically contains this particular list, which is substituted with moments in terms of the equilibrium values. Okay, so and then we're going to use this. Okay, so if we do that, this is basically the same as before, but then because as you can see there is rho in every term here, we want to simplify things and we say full simplify and solve for it. Then it will give you, it is going to take out things that can be taken common for these terms, and then it is going to give you 136 of rho times 1 plus 3x ux times 1 minus ux minus 1 and so on, right. So it basically gives you a simplified form of the equilibrium distribution functions in terms of rho ux uy, right. These are the macroscopic properties that you have. Now what we have to do is we have to translate this back into the C++ code, right. This is what we are looking for. So to do that, what we do is because you C++ you cannot use, for example, let us say ux square is, you don't write it like that, like as ux square, you write it as ux times ux. So we're going to essentially ask Mathematica to write a for example, for f11 equilibrium is what I want to write, then I'm going to substitute for f equilibrium, and then wherever there is a square term, I'm going to not convert that to a square, rather leave it as a times a, okay. And then if I write that, it basically gives me what is f11. f11 is your rho times 1 plus 3 times ux of 1 plus ux, and then you have 1 plus 3 times uy of 1 plus uy divided by 36, okay. That's what we got. Similarly, I can write f00 like this and then calculate, that's going to give me what is f00, equilibrium, correct. So if I go back to my C++ code, okay, so I have f equilibrium 00 equals rho times minus 2 plus 3 of ux square times minus 2 plus 3 times uy square is all I have, okay, divided by 9. This is exactly taken from here, rho times minus 2 plus 3 times ux square minus 2 plus 3 times uy square divided by 9. Only difference is that here I have used ux uy, whereas in the C++ code, because you are dealing with one location, you have additional xy, which are typically you use ij or xy, okay. So it basically that is, those are the values you have here, okay. That is for your f equilibrium 00. Similarly, we write the equilibrium distribution function values for each of the 9 values we have, right. So I write it from f equilibrium minus 10 and then f equilibrium plus 10, then we write f equilibrium 0 minus 1, then f equilibrium 0 plus 1, then we say f equilibrium minus 1 minus 1, f equilibrium plus 1 plus 1, and f equilibrium plus 1 minus 1, and then minus 1 plus 1, okay. It basically covers all the 9 values that we have for the f equilibrium. Okay, questions so far. So that is the idea for today, but we will take some questions before I introduce you to some little bits of other part of the code. Is the Mathematica part clear, what I was trying to do? Would you like to try it yourself in Mathematica right now?
You can also use some things like symbolic.
Sympy, yeah, I mean, need not be Mathematica, it can be anything else. Whatever symbolic language you want to use, would you like to use and try it out so that you will, sorry? Yeah. This one, yeah. Up, yeah, okay. Even up, okay. Stop me where you want. Sympy is I think open source, yeah, for Python, and I don't know what other open source symbolic software are there. Not much. Correct, yeah. I think SymPy may be used, could be used. Mathematica, we have Mathematica. MATLAB has, but it has a slightly different syntax, yes. Here we're substituting for FFS, replacing the MO variable names with the macroscopic properties, right? Rho, UX, UI. IJ, yes. Well, AB, yeah. So these are the, not because it's 2D, because you have only the moments that come up are these ones, correct? You will get, yes. No, you will still get, no, even if it is 3D, you would get ABC, correct? Yes, you would get M0, 0, 0 and so on, correct? Yes, so once you calculate Fs, to calculate again the velocities, you would again use, essentially you can calculate velocities from here, from the moments itself, correct? I mean, rho ux is in terms of m10. M10 is, from definition again, it goes back to Fij, all these things. Right now, we are only doing the equilibrium F equilibrium, right? Correct? But you would be solving for F distribution functions as you are solving in your LBM. I and j can go from, I can go from -1, 0, 1. J can go to -1, 0, 1. I mean, all the 9 possible directions. C form, what we are trying to do is that, yeah, so C form, so we are asking it to print in a C form, okay, and then F11, right, I am substituting for FF equilibrium, okay, and then wherever there is A square, I am saying don't substitute and then leave it as the whole form, means leave it as A star A, okay, so that it will give us U star X, U star UX star as UX as it is left, instead of writing it as UX square. We may not have done this, but this will simplify your usage in putting it back into the C++ code. That's the idea here. Yeah, we do this for all F. We have to do it for all F's. Like I've only shown it for 1, 1 and 0, 0, but we will do it for all 9 values. And then we go back and substitute. That will give you this code basically, right, for all the equilibriums in terms of rho, ux, ui, and then CS square. But still you would require either moment or u to be calculated so that you can make use of it here in the equilibrium distribution functions, because you will come to the equilibrium. So for example, okay, correct, yes. See, for example, here I have calculated, before I came to F equilibrium, I have calculated what is rho, what is ux, what is uy, correct? Rho is nothing but sum of all the distribution functions. Ux is nothing but whatever the distribution functions that survive, right, depending on +1, -1 and 1, 0 for A and B. And then ui is again all those 6 values, okay, that we have here, divided by rho, fine. So these are computed first before I calculated the distribution function for F equilibrium, okay. That means here I am using these F's are the distribution functions which are constantly evolving as you are solving, and from that time step of F values I am calculating what is rho, ux, ui, and those rho, ux, ui is what I am using to calculate the equilibrium F. And then we would do, after this we would do the streaming, collision and streaming. So we would do these steps, correct? That means you calculate macroscopic quantities, you calculate equilibrium distribution function, then you do collision, then you do streaming, and then repeat this step, right? The only steps are streaming and collision, but then collision requires you to calculate equilibrium, because your equation will be like F equilibrium minus F times the omega plus the distribution function, correct? Yes, of course. Yes, 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 it is. Because you are storing 9 directions here, correct? So you have to store for 9 values at every grid point, correct? And on top of that, you have also stored 9 equilibrium F values at each and every grid point. Of course, yes. No, I think probably in the theory you will learn that these lattice directions have to satisfy Galilean invariance properties. So I don't know whether probably that is.
Here, you could have just one in it. Yeah, so this would give you what we call the D2Q5,
Yeah.
if we have the non-moving part. Now what we discovered is that we have particles colliding like this. So the only way that they could go out would be doing nothing, or they would go perpendicular to this, right? And there's no other possibility. For example, if particles would come like this and like this, they would have to go on, because otherwise there's no momentum conservation. So with this configuration, it is actually impossible to distribute momentum laterally to its direction. So if you have momentum in the x direction, yeah, and you turn this around, this here has no more momentum in the x direction. So there's no possibility in this to carry this away. So what you can do, if you are not interested in momentum, but you only solve a diffusion equation, then you can use this lattice. Another possibility, as I told you in the first lecture, was that you use something where things are not quite Cartesian, but you can use, maybe it's too far away, you can use an hexagonal grid like this. Yeah, so they would always be, they would continue on like this, and in this it is actually possible to carry momentum laterally. And so if you use this configuration, even if you have no resting particle, so only 6, so the 2Q either 6 or the 2Q7, yeah, so if you have a resting particle here, then you can do lattice Boltzmann with this. It's actually possible.